we have to finish the last class, right? Because we haven't done the probability,
Right.
correct?
Yeah.
Yes. So, well, let me explain a few things. Since our last class, I received about 45 emails. Or people saying, look, the link's not correct, or look, I'm on the waiting list, I would like to participate, I'm not sure if I'm on the waiting list or not. And unfortunately, at Princeton School of AI, our back office job is not very efficient. It's usually more. But I was able to reply a few in today. So usually I prepare those classes the same day that I teach. So I take Tuesdays to prepare the class. I come here to Princeton, I'm living in Philadelphia, and get everything up to speed. So I fixed the link. Someone changed a few things, so it wasn't working, and I finalized the project. So let me get this here first. And now I'm so this is the correct one. Let me post this in our Okay. But this one, you're not going to be able to copy. I sent you the link of the code, but you're not going to be able to edit it due to obvious reasons. So you can consult this and you create your own
Copy, yeah.
Can't edit it
It's not working.
because
So 1, 2, 3, 4. Try to put the big number and appears another asking for the security. Okay. Okay, so we're going to finish last class, and then we're going to random forest. Probably random forest. I'm not going to say that it is the most important algorithm to learn regarding machine learning, but definitely is one of the top 3. And the reason is you can explain what is happening there. You can
not giving us the permission when I click the link.
Okay. So yes, let's start. So that's what we're going to do. We're going to finish last class. We're going to find the probabilities of the different products for different ages. Yes.
Do we really need probabilities? I mean, if the question is, what's the most likely? And the probability is, you basically say, you take how many they bought and divide by total. So total remains the same, right? So if you know how many they bought, the biggest number gives you the biggest probability, right?
But it is different. The total is different between ages.
Fine.
Yes.
But basically, you know, for every age group,
Yes,
you basically say, well, which ones they bought the last
The most.
the most,
Yes.
right? And that's going to be what they're going to be buying expectation of
That's a very good point. If we were looking only into one age, we would use the result, but actually, as we're going to compare ages, we need some ratio.
All right.
And then that's why you put the probability, you put this ratio to be able to explain that. Let's go to the bottom. Alright, this is the guy. So the question that we had was, yes, okay. All right, so the question that we had was, what are the 3 top products that we would recommend for each one of the ages? The idea is to recommend products. How we would recommend products. And there are more efficient ways of doing that, but only with some descriptive analysis, we will be able already to draw some insights. Last class was all about this, to understand a few things that are not obvious. And this result here that we have, if you run this code, you're going to have this result. So let me zoom in a little bit. No math, correct? Okay. So the first thing that you're going to see is something that it was more or less in line with what you were saying. We are going to have only 3 products, regardless of age. So in total, we have 20 products, 20 different categories. But here, it only appears 3. The category number 5, number 1, and number 8. And that's true for every single age. 8, 5, 1. So that's the pair. Why is this happening? Because for every single age, we're talking about Black Friday. So probably 5, that is the most common here for lower ages, is going to be electronics. Probably. I'm assuming, but it makes sense. And the same thing for 1 and 5. Those are main products. And as we are using the total number of purchases of that category divided by the total number that age bought, we are going to find that those categories are most common. And we were expecting that. What I said is clear? Yes? But there's a very interesting thing happening here. From 0 to 17, the category number 5 has 29% chance. The same thing, now it drops a little bit to 28, it drops to 26, 26, 25,
And I'm back.
and 20, 24, 25. Now, the category number 8, it is 15%, then it goes to 18%, then 20%, and 21%. So it goes increasing, now 23 and became the second favorite category, starting on 46 years old. Finally 23, then 24, and finally 29%. So you had a change, you had a modification, and you were able to grab this kind of a different trend only with very simple, without using any kind of machine learning or statistics, naive analysis. So you see that the category number 5, it's going to be more appealing to younger customers, while the number 8 is going to be more appealing to older customers. We don't know what are those categories, but those are. This result is something very important for you to put on your analysis spreadsheet to send to your boss. Questions, comments? Yes, please.
Are you saying that the .288 is, what is that? That is the product, the probability of buying a product within a category?
Yes, that's the probability. So, okay, let me change a little bit.
So the,
Now, as a data scientist, we are going to receive, someone is going to enter your website. And you're going to collect some information. So we're going to have a bunch of information coming, cookies, so we know the path that this customer went through before entering your website. So if this customer went to, I don't know, Rolex website, okay, so this guy has some money. The information that we have in this case here that we are using is just is just the age.
Like
just the age.
click rate by age category, something
Yes.
like that?
So that's just the age category. Now, we do have a database of previous purchases. And within this database, we can draw some insights, and that's what we've done last class, to draw some insights with very few characteristics. So we had city category, we had gender, we had how long did that person live in the current city, age, of course, and so that's it for our
So I'm just asking specifically, so 26 to 35, colon, what's the first number, what's the second number, the first tuple, the second tuple?
Yes. So what we did here, what this code does is, for each one of the age categories, it outputs the three most
The top three,
purchased
okay.
products.
How many products total?
So those are the products that we have. We have over 500,000.
So it could be significant. I was going to ask if it was the .28 is statistically different than .256, and the answer is probably.
Probably.
Because of what you just said, yeah.
So, but the interesting thing from this, so we just have three categories being ranked as the top for each one of the ages. So probably those are very common products for Black Friday. There's going to be data sheets, electronics for sure, definitely. But this, those kind of products changes with the age. Now the number 8 is more appealing to older customers, and the number 5 is more appealing to younger, and so on. So what we have, so this, what I'm saying is, this is an important insight. If a person enters your website, you only have one information, age. That's the only information that you have. You would be able to actually recommend a better product than if you didn't do this analysis. You would recommend a product number 8 instead of the number 5. That probably, if we just do a general analysis without dividing by age, we would find number 5. So that's the point. We are being able to actually make this more refined. Okay? Okay. Yes, Brian.
So in this, I'm sorry because I haven't looked at the database, but in this database, do you have a lot of clicks per category, or do you have a lot of zeros? Because one of the things I ran into when I analyzed the internet database was the sparsity thing.
No, we don't have any NA. It's every single column is used. We don't have the problem of sparsity because that's not usage. Imagine what he's saying regarding the problem of sparsity is. Imagine Netflix. So Netflix, whenever they're going to recommend you one movie, you have thousands of movies, thousands of possibilities. And you've watched, I don't know, let's say 10. Now with those 10 movies, Netflix is able to actually classify you into one cluster and say, look, this person probably likes this kind of movie. And he's going to recommend you one movie. Now what Netflix does is, imagine that you have here columns for every single movie. Movie 1, movie 2, and so on, movie 1000. And here it is 0. So client 1, client 2, and so on until client 500. Now, this Netflix has a database that indicates if a given client watched a given movie. Now, you can imagine that, of course, not nobody, but most of the people hasn't watched every single one of them. So this matrix has a lot of zeros around it. And so on. So this is not a very good. This is very hard to deal with because you cannot find a lot of patterns. What you're going to be able to do, imagine that this person watched this movie and liked very much. This one liked the movie number 1 very much. 0 and 1 here. So I know this. This person, the number 500, liked the movie number 1 very much. And watched the number 1000, the movie 1000, and liked it very much as well. This first person enters again into Netflix. And what Netflix does is, he finds the people who is most similar, who are most similar to you, and see the movies that those most similar people watched. If you like this, he's going to recommend you this. That's the idea.
You know, I'm sorry. I was thinking of ad tech database. This is a historical purchases database.
Yes.
Okay, never mind.
No,
So everybody's-
But still good explanation for, this case. I mean, he asked you different question, but I think that, your digression was very helpful.
Yeah, no, the problem, the sparsity matrix problem is one of the, you have to be very careful with it because it's very common. Now, I mentioned cookies, for example. So imagine every single website that you're going to receive from the cookies. So me, Vinicius, I'm Brazilian. I have my soccer team, Flamengo, and I enter Flamengo's website. Whenever I enter, let's say, Beth and Beyond website, they are going to receive this information that I enter Flamengo. It's going to enter their database, and they're going to create a new column called Flamengo. That I'm going to be the only representative that probably. Probably there are some other Brazilians as well. But so you can imagine the quantity of columns that are going to be added and the number of zeros that appears. So that's the curse of dimensionality. This is one topic that is going to appear a lot whenever you are studying machine learning, the curse of dimensionality. Every time that you increase one variable, one kind of information, your database increases. The data that you're using to store, the memory that you need to use to store that information is going to increase a lot. So you'll have to find better ways to save it and not doing this. Yes, please.
So you're gonna have more. There are more movies gonna come up every day, right? So they're gonna have more columns added to that database. Is that
Yes.
what you're saying?
Yes. So one big research, one hot topic on research is regarding sparsity. How you do machine learning, taking into account sparsity. You're going to see it if you go to sklearn. That's very important to. That's the best package we're going to use. sklearn. We are going to use this package today. That's the most important package in Python for machine learning. And they have a very good standard to how do you say this? Every single model that you're going to use has the same structure. You're going to call, there are some parameters, it looks the same. We're going to do that with different models today, different random forest. We're going to use decision tree and then random forest. But you're going to see that the structure is the same, and it's going to be the same for every single model, which is great. In the advanced class that we're going to have, Machine Learning 102 or other classes, we're going to learn how to use pipelines. You're going to create your own class. So you start to create ensemble models, but that's for later. But this is only possible because there is a very standardized structure. And you can modify this. You can modify the things inside to get the results. It's beautiful. sklearning, it's beautiful. Okay.
Okay.
Yes, please.
You said curse of some memory. What memory?
Dimensionality.
The curse of dimensionality.
Dimensionality. Okay.
So the
Yeah.
whenever I got the database, I call it pandas.read table. This comes to my RAM memory, my temporary memory. So there's a physical place to store that information. And if you increase that a lot and you start to do operation with that, this falls apart. Actually, I have this problem here in our class. You're going to see that the test, the scoring that we do, the test size is going to be very small because it couldn't handle bigger size due to lack of RAM memory. So you have to.
Yeah, you need to start looking at generators and NumPy matrices. Go to SciPy and see if you can get.
That's written on.
Yeah.
So where do we draw a line where the Spark is very high and when you want to go linear model or PCA model? How do you decide?
That's a very good question regarding PCA. What is PCA? PCA is principal component analysis. It's a way to reduce dimensionality. Yeah, we're going to have PCA next class because it's very important. There are other ways to reduce dimensionality. In this case here, usually you don't use PCA because you have to normalize things and this crumbles apart. But we had this problem in our time series project. We had 64 columns describing an ETF series. So we had moving averages, momentum indexes, so 64 columns. And we decided to do a PCA to actually improve our efficiency, the code's efficiency. Where do we draw the line? We draw the line when, depending on the capacity of our computers. It's always better to have more, not going to say that, but usually it's better to have more columns, to have more information. Whenever you do PCA, you're losing a little bit of information. So the computer capacity and the size of your data. Now, it's going to vary depending on those cases. That's, for example, if you do self-driving cars, they do a very rigid, they do a lot of PCA because they collect a lot of data. And if the algorithm takes too long to make a decision, has to look to a bunch of variables to make a decision, the car crashes. So you have to make this as most efficient as possible, because you have to be able to drive. Now, in other situations, like I was using a face swap, the face swap app. I haven't done no, I have done some PCA, but I could do more. But I had time to train and left it overnight training. Okay, so we finished last class. So descriptive analysis. We draw some very interesting insights, and the idea would be for you to tackle other problems. Try to see if you find other problems. Okay. Now, before we start with our class, let's see if someone asks a question. Before we start the next class, I received a bunch of emails of people wanting to do some capstone projects. Now, we've done capstone projects here, the entire class, and I believe that the team that is doing capstone projects is a little bit tired of that. But it would be interesting for us for each one of you, or we could divide into groups and do small projects, analysis projects. What do you think about this? Who would be willing to do some small project? All right, everybody. So we're going to start that today. Has everybody signed up the sheet, the attendance sheet?
No.
Where's it?
We didn't.
You did. Okay, who got my pen? Okay.
Not me.
Right.
Let's
run an
algorithm.
So let's try to divide it into 3 teams, 3 kind of databases. This will have to be a bigger project. Okay, what do you think about doing this in groups of 3? Yes?
Yeah.
Okay. We do have marketing, finance, and which third category would be interesting to assess?
Healthcare.
Clinical.
Yeah, healthcare and retail.
Healthcare, okay, healthcare. Right, who wants to do something related to healthcare? 1, 2, 3, all right. Okay, you have a group. Okay,
Oh,
Brian?
Okay, yeah.
I'm sorry, I forgot your name. Children. Yes, children. Okay. Marketing, who wants to do marketing?
Wait a minute, healthcare. Are you talking,
Project, the database.
oh, just,
No, it
yeah,
is a very
just
simple
the-
project
yeah.
where we're going to make an analysis of a database. A very simple analysis of a database.
And the domain area is healthcare.
Healthcare, yes.
Okay.
Now it's up to the group to decide which database and which analysis to do. Now marketing, we have 2 groups already. That's it.
Oh, marketing.
Who wants marketing?
Retail.
So we have 2. Right, so 2, 3, and you 3.
Okay.
Marketing. Right. Now finance. Okay, so we have 3 as well. And any other topic that you would like to assess?
Retail.
Sorry?
Retail data.
Retail.
Retail.
So, yeah.
You work together with retail.
It's easy for us to do it.
Okay, so retail, yes.
Yes.
So in our last class, we are going to have presentations of those groups. Later, I'm going to ask you for you to send me an email with the interest that you have. You can get together after the class, so you can combine some way to get to exchange contacts. Okay?
How about keeping a Google sheet in this, and a column there?
I'm going to do that. It's because I don't remember the groups that I assigned.
Are we doing it on Kaggle or where?
Sorry?
Are we going to pick the data sets from Kaggle?
No, that's one of the challenges. That's one of the things. You're going to choose the data set that you want, that you would like. And I'm going to send some different data sources. So we have Kaggle, I've shown before. You have University of California, Irvine, UCI. It's very good. They have very good databases and some other sources as well. Okay? All right. Randall Forest. Okay, so again, you are here, you click File, save a copy in Drive, and this is, you're going to have your own copy that you can change, you can modify, you can do whatever you want with that.
This just uses the same data set, right?
Uses the same data set, yes, uses the same data set. The goal here, look, it's 7:06. I'm going to go, probably this is going to take half an hour. And then we are going to get into the group organization and finding the data sets so we can start working. Okay? Yes. Of course. Are you in this page here? So you click File, you come here, save a copy in Drive, and then it's going to appear creating a copy. Did it? Yes. So now this copy, as you'll have to log in to your Google account, it's on your Google
Right.
Google Drive, yes. So it's with you forever, and you can use this at the assessment of any database.
Yeah.
Here.
Okay.
Here.
Yes.
No.
I'm going to drink some water quickly and be right back. Just a second, please. My mouth is dry. So, okay, for this, we're not going to use Seaborn. We're going to use Pandas. We're going to use NumPy. We're going to use Matplotlib. So Pandas, remember, it's the data structure that creates any kind of data in the same database. It's for databases. NumPy is for matrix operations. So we're going to see arrays, we're going to see matrices. We're going to be working with that. So just numbers, any kind of data. Matplotlib is a plotting package. We're going to use this as well. And now we come here, sklearn. Now this guy is very important. This is the major hub of information of machine learning models and sklearn. You're going to see here every single resource that you need to do a good machine learning algorithm, to provide a good machine learning solution. They do have a lot of, the community is huge, so you can ask questions, they're going to answer fast. Pre-processing, usually this, we're not using this because our database is very clean, but usually this is something that we use a lot. At pre-processing, we have scaling. So scaling, you're going to have the Emacs, kernels, normalization. So basically, whenever you get an ugly database, you're going to have to modify it a bunch of different ways. Remember, garbage in, garbage out. This pre-processing data, this library is going to be important to do this. You're going to have, for example, you have here PCA. And the rest, you're going to have different kind of machine learning models. Clustering, regression, classification, those are different things. Those are different objects that you have. And you have a bunch of algorithms to deploy the solution. Let me see if I can just remember something. I can find this. There was a really good image. Here, this one. All right. This is important. Scikit-learn algorithm cheat sheet. That's very good. So we start here. If you have lower than 50 samples, get more data. If not, you continue on your path. Predicting a category. Are you looking for categories? If yes, you come to this side. If no, you come here. And so you're going to end up with regression, dimensionality reduction, a clustering, and classification. Let me put this link here in our meetup page because that's very important. So you start a project. Right. So you start a project, you don't know, you say, okay, I have over 40 different algorithms that I can deploy. Which one is most used for this given question that I have, the answer that I want to provide. Am I trying to do a regression? Then we come here to the quantity and the number of samples. It's important as well. It's one of the factors to make a decision. And then you are going to enter here. Should I use an SGD, Lasso, SVR, support vector regression? What should we use? Now this map shows you this. That's very interesting. That's a very good tool to have in your tool belt. And basically, this is a decision tree. That is the subject that we're going to discuss today. So you are going to choose the path that is most suitable to you. This, let me go back here to our class. Okay, we're going to look into two models, the tree and the random forest. Decision tree and random forest. What is the difference between both of them? One is one tree, the other is a bunch of trees, a forest. That's it. So we're going to go through trees a lot because the concept, the random forest, the difference is you're going to input the number of trees that you want in your forest. They are going to train a bunch of different trees. They're going to make a bunch of predictions and take the average of the predictions. That's the difference.
Why is it called random forest?
You have, because the way that you collect the trees, let's say that in our case, I think that we're doing 100. You randomly choose chunks of the data to train every single tree.
But tree meaning the node, the root node, or the whole tree?
No, the whole tree. So what's happening is, let me erase this.
What's this?
We have our data set. Let's say that we have 1,000 rows. Now, what random forest is going to do is, let's say that I have 10 trees. It's going to randomly choose a chunk of one chunk, randomly chooses one chunk of the database. The size of the chunk you can specify as well. And he's going to train one tree. Then he chooses another chunk, the same size, and trains another tree. And so on. He's going to train 10 trees, and he's going to have the output of every single one of the 10 trees. And then he takes the average of those. It can be the average, it can be the most predicted category, but somehow he's going to make a decision of which one of them he's going to choose.
Randomly.
This is not random. The part that is random is this one.
Data selection.
He randomly chooses the subsample of the database. And then he trains a tree. Because the method of training the tree is not random. That's what we're going to go through here. You have a predefined method. You have a randomness of the way that you grab the data, but that's it. Let me run this first. Now we have our database, again, the same one. And we come to our first case. So to start simple, we're going to look only to gender. Let's pretend that the only information that we have is gender and purchase. Okay? Right. So that's in average, females spend 8,000. Let's say that this is dollars, but it's not. But let's pretend that it's dollars. $8,000, and these males spend $9,000, $9,400. This is the top of our database. So we have one female who spent 8,300, some other female who spent 15,000, and so on. Okay. Well, so I have this data set. What we're going to do now? Has anyone have not heard about training set and test set? Who has heard about this? Training data set and test data set. Okay, some people haven't raised their hand. I'm going to assume that we don't know that yet. The way that machine learns, the machine looks into the data and finds the patterns. Now, then we put this machine to work on the unknown. New people are going to enter, and the machine is going to make a classification. But that's new data. The machine hasn't seen this new data before. And you're going to have bias. If you grab your whole database and you train your machine learning algorithm on your whole database, the machine is going to capture every single pattern there. No. This is not the best way to train the machine. Because the best way to train is you grab a chunk of the database, you train on a chunk, and then you evaluate in a data that this algorithm hasn't seen before. Because you want to see how the algorithm would perform in a new data. Now that's the test set. So you have the training set and you have the test set. Depending on the results, you're going to tweak your machine learning algorithm. Now let's pretend, let's say that you train your algorithm, you train your machine learning algorithm, and on the training set, you have an accuracy of 95%. And on your test set, you have a 50% accuracy. What does that mean? I ask you.
Algorithm didn't learn properly.
The algorithm didn't learn properly. Yes, that's true. What happened here is that it looked into this data set and it grabbed not only the patterns, but also devices.
What's the 90%?
Patterns that are not actually patterns. They are just something that happened. For some reason, it happened a lot in this data set, but it's not what is true for the world. Now, what should you do whenever this happens? You should, this means that your algorithm is too complex, it's too big, it's grabbing everything. And he's not making good decisions. Let me show you a different graph. I don't know what is this website and which one is this. Remember
Does your training data set keep changing or it's constant?
okay, sorry?
Your training data set, the data inside the training data set, you keep updating that or it's a constant?
Yeah, are you doing a cross-validated?
No, that's this is going to depend in how many data you have. But I'm going to get there soon. Just
Yeah,
let
if
me
it's time
let me
series,
put this.
You can't do that on time series.
Let's say that we have this situation here. Remember the basic statistics class? If you have, the best model to have here would be like this, correct? This is what you are looking for. Now, this would be something like this. You have your y equals alpha plus beta x. That's a linear regression. But what I could do this. Beta 1, beta 2, beta 3, x3, beta 4, x4, and so on. If I do this, my model is this, my model is going to do this. It's going to come here. that's an accuracy of 100% in our training sets. It's very good in our training sets. The problem is whenever appears a new data. So you have here your X, you have your Y. Something appeared here. It's going to say, here. So that's the result. This one, this is going to be the result. Because it's grabbing every single information and not the pattern. And it's going to make bad predictions. So you have to decrease the complexity of your model. Now, if you were to have a database like this, if you fit a linear regression, you're going to have a model like this. It's not going to be good. So what you do, you increase, now your accuracy on your training set is going to drop dramatically. What do? You increase the complexity of your model to actually try to get other patterns. Now, this guy grabs this. So whenever you fit an algorithm to the training set, you check the accuracy. And you compare with the accuracy of the test set. You're going to have, and that's the majority of the cases, in real situations, where you're going to have 10% here, 9% here. 10% for the training set and 9% for the test set. What does that mean? Is this algorithm good? This means that the algorithm that you have is actually within the algorithm capacity, is grabbing the most information that it can, is with a good behavior, but within its capacity. Is this something that you would put into production? Depends. Sometimes. I'm going to give you an example. That's a real example. Do predictions for failures on electrical equipments. That's predicted maintenance. The company's accuracy, 33%. So that's the first thing that you do whenever you go to a client. You ask, what is your accuracy? What is the accuracy of your algorithm, of your, sometimes it's not an algorithm that you have, but the process that you have for making predictions. And he's going to say, we don't evaluate that. You have to evaluate that because the result that you're going to render, you will only be able to say that if it is good or not if you have this benchmark. So 33%, our first algorithm that we developed, 58%. 1 month. 1 month, 58%. 1 year after, now we are in 83. That's much better than 33. Now, in 1 month, we jumped from 33 to 58. And it took us 1 year to increase 30 points. Because you have now the first patterns is simple. You just add some complexity, you put a different algorithm, and you're going to be able to capture some patterns. Now, from here to 80, that's a little bit harsh. From 80 to 90, details. From 90 to 95, that's $1 million prize for Netflix. But it is important. Okay, now regarding how do we select the training set and the test set? Do you have some questions here? No. How do we select those? You have some strategies. Of course, randomly, please. Everything that you do it randomly. There are 2 ways to do that. What should I remove here? That's where it's done. Right. You have here your whole data set. Now, the way that I did here was randomly selecting some rows. Let's say that I randomly selected some rows, a proportion of 95%. So I'm grabbing 95% of the data and training on those 95%. So I grabbed everything here, this guy here, I set aside to test my algorithm. Is 95% good or bad? It depends on the size of your data. In our case, we do have 500,000 rows, more than 500,000 rows. So we have a lot of rows. We have a lot of information. 5% of 500,000. How much is it? 500, 25,000. 25,000. 25,000 rows. It seems good. It depends on the number of categories. The ideal, usually you split 80-20, 75%, 25%. So it's going to depend on the size of your database. You have to have a very good size of test. But remember, that is machine learning. You have to teach the machine. So the idea would be to have as many training information as possible, because you need to grab patterns. That's one strategy. That's the strategy that I chose. There are others. There is another strategy that is very common. That is called cross-validation. How does that work? You're going to divide your whole database into chunks. Let's pretend that we divide it here into 5 chunks. Right. I had another one here already. So 1, 2, 3, 4, 5, 6 chunks. What you're going to do is, you take the first chunk, set aside, train your algorithm on the rest, and test here, and check the result. Based on the result you're going to see, then you set aside the second chunk, integrates the first one, and you train on those other 5, and test on the spare one. And you go rotating this. That's another way to do a train test. Yes, please.
But wouldn't that be similar to what you explained earlier, like a random forest where it randomly picks up the data set, right? Or is there some difference?
It's in this case we are rotating. In the other case, the random forest, it just grabs a chunk. It might repeat. This case doesn't repeat. So this guy here, he's outside. He's outside. This information is not going to be able to. When I integrate this, it's going to be picked up. On the random forest case, it might be the case that one of those rows are never going to be picked up. Randomly, you choose. By a very small chance, you might choose every single row again. This chance is positive.
Does it make a difference if the data is structured like a table, which is one to the other, or it depends on the category, or when you decide you're going to go for cross-validation versus reinforcement?
Mostly, you're going to make this decision based on the size of your data. Why? Remember that graph that you had the possibility of having, let's say, 500 data, less than 100K, less than 100K, less than higher than 10K. So let's say that you have small data. And you have to teach the machine, so the machine needs to get and needs to understand what are the patterns. But you have to do that in a way that it doesn't grab the devices. You put this strategy. Cross-validation. If you have a lot of data, randomly select a chunk and move forward. Now, in this cross-validation strategy, it is very important to set aside, again, one small chunk, but this time can be smaller. And this will be, no, it's a definition of the validation data set. You can use validation tests and training data set. But you have to set aside a small chunk. Why? Because when you do cross-validation, you're going to be training. The machine is going to see every single data. He's going to see every single data. So there's a chance that he's going to get that pattern.
Where do you define this in the algorithm? Which one to pick? Is it the cross or the?
I'm sorry?
Where do you define the algorithm, like to pick one of these?
How to choose one of these strategies?
Yeah.
Where I define it? Well, I would choose based on the data size. Here, I'm using train test split.
Oh.
But you could, model selection, probably you're going to have the cross-validation structure here.
The diagram that you were just showing, that machine learning thing, right? Where do we see cross-validation here?
Now that's once you chose the algorithm, you're going to choose the strategy. This diagram here is for you to choose the algorithm that you're going to use.
Right.
Now, within the algorithm, you're going to have a structure. And it's going to depend on the case. It's not here. I don't think it's here.
No, it's not here. I was trying to find it, either cross-validation or even the.
Cross-validation is not an algorithm.
Oh, okay.
It's not an algorithm. So you're going to say, let's say I'm going to use random forest, for example.
Okay.
I'm between random forest or support vector machine. Let's see. K-means, support vector machine, K-nearest neighbors. Okay. So I'm between support vector classifier or K-nearest neighbors. So if this guy here is not working, I come here.
Mm-hmm.
Here, okay. Linear support vector and SGD. Now this is going to depend on the size of your database. You're going to choose one or the other. Once I chose this, now I'm going to construct what we're going to do today. And you're going to choose the best strategy to deal with the data. If cross-validation or just a simple split. One thing that you're going to see is that everything that we're discussing here, the way that you're going to treat the data, it's a hyperparameter. You can choose, you can try both. Try both. And see what has the best accuracy.
And then you go with you have like a training set, and then you have a.
You can try. The problem is, for me, what I'm saying is, imagine that you have 1,000 rows, 1,000 information. If you're going to do 80% and 20% train test split, you're going to have to. Then this 20% is a lot of data that you're not going to train with. So there are a lot of patterns that you're not going to capture.
Mm-hmm.
So in this case, I would say, look, you might even try the train test split, but probably the cross-validation is going to work better.
Why don't we take the full data set to train the model?
That's a very good question. I'm going to come back here. Whenever you train on the full data set, you're going to grab devices of that data. The machine is going to try to capture every single pattern, every single thing that happens. And when you do that, there's some randomness that the algorithm is going to try to capture. If you do that, let's say that a new data appeared that hasn't appeared before. How is the machine going to be able to capture that? It's going to be a little bit easy. I'm going to show you again this. Let me put this chart in. I love this one because I think it explains a lot.
That's what he's talking about.
Right.
It's
We have a bunch of data.
simple.
Correct? What we would be doing if we were to split between train and test is to eliminate some of this information randomly, but the pairing continues.
Can you explain the purpose, because I missed the first part? I am very limited background there, so is it about training the model? And data set, we have to build the model, we have to train the model.
Yes.
That's the problem.
Yes. I've chosen one model already, and I'm going to train this model. I believe that our random for this here, a linear regression is going to do a good job. Why? Because I plotted, I look into it and I said, makes sense. I'm good, I'm good. So I'm going to put a linear model. Now, if I put a linear model here, I'm going to grab this, correct? If I train on the whole data, I train on the whole data. Now, in this case, because that's a very simple case. Let's imagine that we have this. Let me see, how can I fit this in this simple case? Now, if we don't know which model we chose, and this is a two-dimension thing, so this is going to be obvious. Now, if we had the model, we're going to see when we construct the model, we don't know the complexity of the model that we are choosing. We don't know that beforehand.
We don't know, so we know we're doing classification or regression, we know clustering, we know the.
We know that, but we don't know, we do know the structure of the model that we are choosing, but we don't know if this is going to fit well the data. Because here we are looking into only two dimensions. Remember the TS problem, the time series problem, we had 64 dimensions. So we cannot look into this well, just like here. So in this case, it would work, we could use the whole database. Imagine that there's a third dimension here that I don't know. There's a third dimension. I don't know what is the pair. So I cannot look into this and see what is the best algorithm that I'm going to fit. So beforehand, I don't know what is the best algorithm. But I have some metrics that are going to help me to get there. Now, if I use the whole data set, I'm going to train a model, and he's going to give me a result. Let's say that he gave me 95% accuracy. Is this a good model?
Great.
It's a very good model, right? If I train a model here in this case that does this, this is 95%. This is 95%. Now, is this a good model? So this model, he's capturing every single deviation that it shouldn't. It's not a model, it's a simplification of the reality. It's not a model. So that's why whenever we have the 95%, we don't know if it is good or not. I'm going to give you a practical thing. Who here is from economics background? So in economics, we do a lot of linear regressions, and we look into the R-square. We're going to talk about R-square here. And sometimes the R-square is 80%. And you say, oh my God, I have a very good model. And then you have this whole diagnostic thing, so you have to plot to see if how's the reality, blah, blah, blah. Those guys here, they thought of something that the economist hasn't, of splitting the data. So you're going to train your model on a chunk. And then you're going to say, okay, so this is the model, it looks good. Let's see the performance of this model in a chunk that the model hasn't seen, before. And now you're going to see the reality. This idea is so simple. That's out of sample testing. But for some reason, the economist hasn't used that. I've done a graduate course in economics in a very good place, renowned place, and they haven't been to this. It's crazy. This is something that is changing inside the economic background when you teach in economics. So that's the reason why you should you do this split. Now the name of this is overfitting. You're going to hear this a lot. You're going to read this a lot. So my model is overfitting or not. So with this, I think that we went through a bunch of stuff, right? Okay, questions?
I think best thing is, if you can go through that example that you want to, so this way we can all start relating this.
Yes, no, let's rock. Okay, so I imported the packages that I'm going to need. I'm going to try two models here. I called one DTR and the other RFR. So this is random forest and this is decision tree. Now, for those who are right, now, decision tree is just one tree of decision, and random forest is a bunch of trees. That's they're the same thing. So we get the database. Okay. So that's our database from previous class. We have Black Friday. We have some characteristics of the customers, and we have the amount of purchase. This is not in dollar terms. We don't know which currency. Now I'm going to go through a first case that is very simple, just so as we can understand what is happening behind here. We are looking into gender and purchase. That's it. When I run this, so we do have female and male. Females spend less than males on Black Friday. So let's rock this. Now let me do this slowly. The first thing that I'm doing here, let me comment that out. Data one dot. I did here something called get dummies. I got was spoken with that. So get dummies. What is a dummy variable? You know, who here doesn't know the difference? Doesn't know what is a categorical variable? Categorical variable. Okay, so we're going to have here different kind of variables. We're going to have numerical ones, the amount of purchase, the value, and we're going to have categorical variables, which are categories. So male, female, city A, B, and C. Now, the computer, those machine learning algorithms, they cannot look into this kind of. They don't look into strings. They look into numbers. So every time that we're going to put some model behind us, we're going to have to transform from categories to numbers. And that's how we do that. We have the gender column with male and female, and now we do have two columns, gender female, gender male, and we have a binary variable, 1 and 0, if it is a female or male. Okay? In pandas, that's how you do it. Get dummies, and it's going to do that. or he's going to see that a given column is categorical. He's going to find every single category within that field, and he's going to put that into columns and 1 and 0s. So we can see another example. Later, we're going to have, I'm showing the good stuff. Okay. So here we have gender, as we see. Now we're going to transform also the city. So we have city A, city B, city C, and the age groups as well. Everything with 1s and 0s. Okay? Yes, no? Okay, yeah. All right. Now, we are going to split our data into train and test. So I'm going to use this package, train test split. So I got this package here before, train test split, and I called it TTS. Otherwise, this is a very large name. I can rename it to whatever I want. So I'm using this, and it outputs the train, the X train, the X test, Y train, and Y test. Another thing. So we have here 2 columns. We have gender and the purchase. I'm going to split this data into X is what are the characteristics that I'm trying to grab to predict the value, to predict something. What I want to predict, I'm going to call it Y. What I'm using to predict, I'm going to call it X. So that's what I'm doing here. This code, it already generates, so I'm using data1 gender as X. So I don't know if I can do this, but I hope so. Not yet. I don't remember how to you set us something like this is going to understand. And now I do have the X train, X test, Y train, and Y test. An interesting thing to see is that X1 train scan dot shape. Let me print this.
It's cool. Yeah, cool.
So now this is a vector. Actually, it's not a vector. You see that in this case, it doesn't have a dimension here next to it. This is something that the output here that we're always going to have this problem of the dimensions that disappears and you have to input. Of course, it's something. But the algorithm doesn't see this as a good thing. That's why I put reshape here. So whenever I do this,
Yeah.
the same thing. But basically, we are going to build. We have an array of numbers. Let's hope that this is going to work. And I do the reshape. I had to do the reshape for the Y in this case. And now I do have So what I'm doing here, and you're going to see that I hope that you're going to be kind of surprised, but we just trained the machine learning algorithm. That's the machine learning algorithm, and that's where we train, and that's where we predict. That's it. The first time that I saw this, I said, that's it. What's all the fuzz about this, right? And then I found out that the fuzz is about the database, not the machine learning algorithm. To train a machine learning algorithm is very simple. You're going to need 6 lines. The machine learning itself is very short, it's very quick. The hard part in a data scientist line is the database. To get the database adjusted properly to whether a machine learning algorithm. Because sklearn did a very good job putting standards on the way that you construct machine learning algorithms. It has a pattern. You're just going to need 3, 4, maybe 5 lines. If you want to customize, you want to ensemble a bunch of models together, you call a library called pipeline, and you're going to increase so 1 line, and let's say that you're going to put 4 models to work together to make the prediction. You're going to put this in 7 lines at most. It's that simple. It's that simple. Of course, the only thing that you have to understand is what's happening behind this guy here. And that's our class. That's what we're going to discuss. Now, let me enter here. Let me go back to my lines. Of course, what is the best tool for a data scientist? The tool that makes every single data scientist fantastic. Google. You Google everything. You're going to spend the rest of your life Googling stuff. It's Google and what? It's true. Come on, that's not right. Yeah. What's the name of that thing that solves problems? Stack Overflow.
Yeah.
Google is going to lead you to Stack Overflow. That's what's going to. I just summarize your life as a data scientist now. So if you Google sklearn and Forest. Oh, no, sorry, we are using this here. Okay, Google it.
Stack Overflow.
Correct. Okay. So here is everything that we can use as a hyperparameter to make our model better. And every single model has a bunch of hyperparameters that are going to be important. So we have only 6 lines, we do, but we have a bunch of things to go through to actually decide. Of course, that sklearn provides us with a default situation that works most of the cases, but we will want to change some things. Criterion, mean square errors. Who here doesn't know what are mean square errors? This example is good. What time is it? To 8 o'clock? It's 75. 7:55?
Yeah.
6:30.
Until time to cover. What is that?
The whole model, everything. Everything.
That's why I wanted to say last
5 minutes. Let me ask you something here, and please be very honest. Who here learned something new today? I'm happy. We're going to wrap up. You know, when you're having fun, you're. Mean square errors. It's because we went through a lot of important concepts, just like mean square errors. They are going to appear again and again. let's finish. Let's wrap up with this. Then. Let's. Oh, I have a very good graph. Yes. Ah, weren't expecting this. Okay, this takes a while to run, but basically, whoa, right? That's beautiful. What is this? The optimal point. The optimal choice. The choice that lowers the error. That's the minimum error that we're going to have from this data set, which is huge. That's the error. How do we find that? Now, first, how do we define error? So mean square errors is basically you'll have the sum y doesn't matter, y hat, that's our prediction, square divided by n. That's a yi, that's a y hat y, what I predicted, minus what is the actual value. I squared to make, if you do a small error, I'm going to make a punishment. If I do a big error, as I'm squaring it, putting this very heavily and punishing this a lot. And I take the average. That's why I do it. It's not because it's a bad thing, it's the average mean. Okay? So that's mean square error. Does that make sense? So if I'm making mistakes, here in this case I'm not making mistakes, but if I'm making mistakes, I sum that up. And the goal is to find a model that is going to make predictions, that is going to minimize this.
When you minimize this, do you maximize the accuracy?
So that's what's happening here. The model, I'm putting different models, and he's trying to find the choice that is going to minimize the loss. And this is going to be, that's, I have to sum up to 5,000, but that's 8,000 and something. So basically what this says is 8,000, so we are looking only into male and female, right? And in this case, if I'm not mistaken, I'm checking the field. Okay. So our model, he's making this guess for females. Let me see. Gender male, so gender male is 0. Whenever gender male is 0, meaning it's a female, he's going to guess that this person is going to spend $8,700. Why is he doing this? Remember, I'm only looking into male and female and trying to make a prediction. So he goes to the every single expenditure of females. He looks into the series, and he's going to find the value that minimizes the loss. In a situation like this, in our case, what we have is looking terrible right? Just to finalize our class, we have here the female category, we have here the male category, and here's the purchase value, and we have a distribution 500,000 rows. Okay, it looks good.
What is we trying to do here to predict how?
Every single point here is one purchase. So this female expanded, I don't know, 20,000. And this, so in average we have here, let me put this 15. This is going, the average is 8,700. For male, the average is a little bit higher, 9,000 and something. That's what we found. So that's the distribution of the data. What the random forest is trying to do is, where's the green? Is trying to find, so a new person entered the website, and the only information that you have is that it is a female. What is the prediction that you're going to do, you're going to make for the expenditure? You only have one shot.
So is the outcome of the knowledge of how much this person will spend?
Yes.
Based on what?
Based on, in this case, gender.
Just-
Just gender. So in this case, he's saying that is 800. And for males, no, of course that's actually the average. It's exactly the average. Because I'm only using gender, just one category. And if we go here, we have the averages when we did the description. So that's the average of each one of the groups. And then I just put it, I said, look, you know what? I'm going to test if this is the correct one. That's actually what the average is, the average, the value that lowers the mean square error. What I did here was a for loop, starting in 5,000 until 10,000. And I go for every single 5,000, 5,001. It makes this prediction, 5,000. And see what is the mean square error. 5,001, what is the mean square error? 5,002, and so on.
So how do you know the prediction? You only know the actual.
No. So this is a dumb model. I'm just putting numbers to see the mean square error. If I were to predict 5,000, which would be the mean square error?
Sorry, I thought the source of data, this distribution is real, it's actual data.
So that's in red we have our y. In green we have our y hat. So I'm saying, no, don't look into this. I'm building another model. I'm saying the model is every single female is going to spend $5,000. How wrong will I be? And if every single female spends 5,001 and 5,002, so that's the for loop that I'm going until 10,000. He looks at every single number and he appends here into mean square error values. And I print in the end the optimal index, the index with the lowest value. Guess which number it would be. It is exactly, here starting at 0, but I started at 5,000. So it's going to be the 8,700. So that's the chart of the minimum of the mean square error.
So for 5,000 is y, 5,000 is y hat.
For y hat as a 5,000, this is the error, right here. 5,001, it's a little bit lower. 5,002, lower, and so on.
What's the y with the y hat?
No, here is just this chart here is mistake by prediction. And it starts at 5,000, because I started the for loop at 5,000. So here's 5,000, 6,000, 7,000, 8,000, 9,000, 10,000. So whenever it puts as a prediction 5,000, it calculates the differences between each one of those points in 5,000, squares, and takes the average. And this is the result.
So that's 5,000 minus 8,700 divided by.
No, the 8,700, this is the prediction for the random forest. What it does is 5,000 minus this 3,000 square, plus 5,000 minus this square, plus it goes through every single y. So remember that the mean square error is the sum, and adding up, let me put this in a different way. The mean square error is, let's grab the 5,000 example. 5,000 minus y1 squared plus 5,000 minus y2 squared plus plus 5,000 minus y 500,000 and something squared. So I'm summing this up and dividing by n, the size of it. This number is this guy here, this number.
Yeah, okay, got it.
When I put 5,001, lowers a little bit. 5,002, 5,003, 6,000. So it's improving. My algorithm is lowering the error until it reaches a minimum. The minimum is 8,700 and something. That is the prediction of the random forest. So the random forest is not that it is doing a for loop through every single number. Actually, it inputs a different strategy, and they reach the same result. So it's a different strategy, but it reaches the same result.
So if I were to do the cross validation for the same data set, I just take that one argument, that's it.
If you were to do cross-validation,
Instead of MSE, that line, decision tree. If I take out MS,
Mean square error.
Yeah, mean square error.
this would be a different error measure. Therefore, this is going to be a different optimal point. Why? Imagine that we are dealing with absolute errors. Instead of squaring it, it's not. So this means that small mistakes and big mistakes, they are punished by the same weight. This usually leads to a different result. In this case here, it would lead to the same result. But we could, let me think of a different algorithm. Let's say that I simply don't care for outliers. So my error would be, if the error is above something, just don't care for it. It will be the inverse of the mean square error. It could be as well, because I don't care for outliers, this doesn't happen often, so I don't care, just care. This would reach a different optimum as well. So one of the first discussions that you do whenever you're trying to make a data science solution, create a data science solution, is what is the error that I'm going to try to diminish? And I'm going to tell you why this is important now. Imagine this situation, you're trying to classify dogs and cats. If you make a mistake, you can make two mistakes. You can say that that something is a dog, but actually is a cat. Or you can say that it's a cat and actually is a dog, correct? In this case, it kind of doesn't matter. Let's say that I make a classification of an image that predicts if it is cancer or not. Now, the situation is different, because if I predict that it's cancer, but it's not, it's one situation. But if I don't, I say, no, it's not a cancer, but it is, that's terrible. So in this case, I have to put more punishment whenever I make a false negative. I say that it's not, but actually it is. So this is going to render a different optimum algorithm. So we are going to have this debate regarding what would you like. You're going to make mistakes. The algorithm is going to make mistakes. But what kind of mistakes it's better? Makes more sense to make.
One quick question. How do we use the random forest algorithm in this process? How do we use it?
The random forest.
Yeah.
I use the random forest only on the last algorithm because we have more complexity.
Okay.
But basically, guy here.
Yeah.
I choose DTR.
Uh-huh.
What I would do is our random forest regressor, RFR. And probably there are some things here that are, let's see if everything inputs. That's it. Right?
So in this case, which are the trees here? The tree is the forest, right?
No. Yes, in this case we do have a bunch of trees. And we can output that. So, but of course, in this case, that the very simple case, every single tree is going to be the same. Every single tree. Yeah, we're going to grab different chunks of the database. This might lead to some differences, but it's going to be the same. Now, so to next class, we're going to go through the bigger models, and we're going to see some nice charts like this one here. And this is the reason why random forests are very good. They're not good, they're very good. Very, very, very good. Because usually random forest is one type of algorithm, a very special one, that you can actually see the results. You can actually see the tree. Usually algorithms, people say that it's a black box. You don't know what is happening behind it. You don't have an intuition. And whenever you're going to present this to the client, it's a no. I read this and it led to this output, which is very good. But this here, you can see he chose first gender to display it. Then he chose the seed category. We're going to see how this algorithm makes this decision. Why he chose first gender and not seed. There's a reason behind it. So we're going to understand why this tree happened.
So is random forest only for classification?
In this case, we're using for regression.
Or regression?
In this case, we're using for regression. It's not the best for regression. Okay? Guys, thank you very much. I'm going to find out how to do the groups. But now, I was very impressed. I thought that this would go very quickly. This would be, and yeah, let's see what we're going to do. Thank you very much.